everyone. It is indeed an honor to be here with you today. I am Mohammad Hazhir Mozaffari from the Islamic Azad University of Iran. And today I will be discussing about a single quantum dot photonic crystal-based laser that's working in telecom C-band wavelengths. This presentation is divided into three parts. I will first cover the quantum dots and its potential for use in a laser active medium. Then I will describe offered designs and proposed design for a single quantum dot laser by use of a photonic crystal cavity, and then investigate its modeling procedure and its obtained results, and mainly its lasing characteristics. Now that you're aware of the overview, let's begin with definition of quantum dots. Quantum dots are semiconductor particles few nanometers in size and having optical and electronic properties that mainly differ from larger particles, and because of the quantum confinement. As you know, the quantum dots have bound states and discrete electronic states that is very look like the single atoms. In fact, due to the quantum confinement, the density of electronic states in the quantum dots in conductor is increased, and its continuous states convert to discrete states. Actually, they have a fully discretized density of states, and we can see this characterization here. And because of this characterization, quantum dot laser needs a small number of carriers to realize the population inversion for lasing. And the lasing threshold power can be reduced. In this slide, you can see the advantages and disadvantages of the using quantum dots as a lasing material, or as a material to produce lasing action. You can see that the advantage is lower power consuming, temperature stability, tunability, and miniaturized size. And maybe its challenge our pumping method that may be somewhat difficult. Its fabrication is not very cost effective, and integration the quantum dots with the resonating medium is not very easy for us. And in this slide, you can see the historical evolutions of quantum dot from 1982 towards 205. And you can see that after this evolution in the last decade, some experimental and theoretical investigation have been carried out to observe the predictable phenomena associated with such interaction between the quantum dots and a cavity, some of which are in the study of the interaction of quantum dot with micropillar, microdisks, and photonic crystals, microcavity. Compared with micropillar and microdisk cavities, the photonic crystals cavities provides stronger optical confinement, and in fact, the interaction of the unique properties of photonic crystal cavities, like their small mode volume and their high Q factors, with properties of quantum dots, mainly provide the emergence of a single mode laser with low lasing threshold power. In quantum dot photonic crystal lasers, The non-radiative recombination at room temperature is more than the radiative recombination. Therefore, it is possible to meet the lasing condition at room temperature by increasing the modal gain and by using several layers of quantum dot and also using high Q factor cavity. And actually applying atom cavity system in quantum dot cavity system, even with the resonance wavelengths of the nanocavity and the quantum dot excitons are very different. Significant emission can be found in the nanocavity mode. You can see here that the most experimental studies focused on the gallium arsenide-based laser, gallium arsenide quantum dot laser, which can act in 0.9 till 1.3 micron spectral range. And the quantum communications request minimum losses in silica fiber that occurs around 1.55 micron and telecom C-band. Indium arsenide and indium phosphide quantum dots, due to their reduced lattice mismatch as compared with indium arsenide and gallium arsenide quantum dots, are the promising platform for 1.55 micron for a quantum dot laser that working at 1.55 micron. As shown, the lattice is a triangular, and the device comprises a two-dimensional photonic crystal structure with a triangular lattice. Constant is about 413 nanometer, and air hole radius is about 133 nanometer. That devised in a 200 nanometer thick suspended slab of indium phosphide. As can be seen here, a point defect is introduced into this photonic crystal slab by removing the innermost hole where an indium arsenide quantum dot is accurate. A slab is indium phosphide, and the quantum dot is indium arsenide that's located within the innermost. Good. We know that telecom C-band indium arsenide quantum dots with a medium density are grown within the indium phosphide membranes, and our proposed slab is about 6 periods across by 7 periods long, and have a miniaturized device about 3 micron wide and length. It's worth noting that all geometrical characterization of the proposed device initially obtained from our earlier experience of photonic crystal slabs, and then precisely optimized by use of a PSO particle swarm. You can see here that the photonic band gap of the proposed photonic crystal slab for TE. You can see that the figure demonstrates 3 photonic band gap, 3 complete photonic band gap, PBG1, 2, and 3. Actually, we used 2 of these 3 photonic band gaps to design our laser cavity. In fact, the cavity has been designed to have 2 resonance peaks at the pump and the lasing wavelength. The laser is excited through a continuous TE polarized source at 532 nanometer. And the source is located at the top of the structure and adjacent to the upper surface. And the pump is 532 nanometer, lies within the photonic bandgap tree. Photonic bandgap tree is associated with the pump, and the pump is the pump signal 532 nanometer located with. You can see here that we used two of this photonic bandgap. One is for pump and another for the lasing wavelength. This slide shows the gathering the output light method. You can see here that we have a fiber taper located from top surface of the device, and a one-cyclic coupling is used to gather. Modeling of lasering is described in this slide. The auxiliary differential equation method with the 4-level active region has been used to simulate highly precise version. The highly precise version of the Raman method is exploited for this simulation that include pumping dynamic and the Pauli exclusion principle in this work. This method is actually classified as a semi-classical approach that considers electromagnetic wave in the classical form and considers the active regions as a quantum one. In this way, 4 energy levels, 2 of which are in the conduction band and 2 in the valence band, are considered while the transition of electrons between this energy states is modeled by the 4-rate equation that you can see here. 4-rate equation for a 4-level 2-electron system and lasing system that taking into account the carrier diffusions. Active region dispersion is modeled by coupling this equation together with the Maxwell equations. In fact, the active region dispersion is mainly modeled by coupling these rate equations to Maxwell equation via the proposed method. As mentioned earlier, in our proposed design, the laser cavity supports 2 resonant modes coinciding with pump and lasing wavelengths. This figure shows the distribution of the optical electrical field intensity inside the cavity at the pump wavelength and the lasing wavelength. Part E is for pump wavelength and B is for lasing wavelength. As shown here, the pump signal is completely focused on the quantum dot through which the visibility of lasing is provided for the quantum dot. In fact, the proposed laser uses this resonant mode as a mean to enhance the excitation of the quantum dots and optical pumping. Besides, the bounded mode profile in lasing wavelength, which depicted in figure B, provides the narrower output spectrum. Besides, we calculated the spectrum of the cavity resonant modes. You can see here this curve that shows this spectrum of the cavity resonant mode, in which 2 frequency filters are used for better detection of the selected resonant modes. As seen in this figure, the proposed cavity supports 2 resonance modes at 532 nanometer and 1.55 micron. As a result, both pump and lasing wavelengths resonate with respective cavity modes. As calculated from the spectra, the Q factors of the power and lasing resultant mode are in the order of 10 power 5, and this is a really high Q factor for photonic crystal cavity. The inset of the figure illustrates a zoomed in representation of the laser output spectrum at the pump power of about 100 nanowatt. Clearly, it shows that the lasing peak occurs at the center wavelength of 1.55 micron with a line width about 0.019 nanometer. These very good spectral characteristics show a comparative improvement as compared to those reported for PHC lasers with a single quantum dot gain medium. The dynamic response of the system is also calculated. You can see here in the part A, and the distribution of the carrier population within the quantum dot has been plotted for the 4-level lasing system. As shown in this plot, the population inversion is realized in a very short time, less than 3 nanoseconds. And indeed, this achieved mainly due to the effective way of pumping in which the pump resonantly excites within the cavity. One of the important lasing properties is the plot of the input power versus the output power lasing, or the threshold curve, which has been calculated for the proposed laser by a FTDT simulation. You can see this plot in part B, and as seen in this figure, for the threshold powers about 55 nanowatts, the population inversion occurs and the lasing in a single quantum dot take places. As a conclusion, analyzing the simulation result with regard to the wide range of semiconductor laser describes that the proposed laser, due to its beneficial properties such as sharp spectrum and low threshold power, can potentially be instrumental in practical photonic integrated circuits and lab-on-a-chip systems. Besides, since experimental results for quantum dot photonic crystal laser at 1.55 micron or telecom C-band wavelengths are still limited, the designed laser is particularly promising for future optical quantum communication systems. And here you can see our related publications about 4 ISI journal that published in this regard. Finally, I would like to thank conference staff for organizing this event, and it is indeed an honor to be here today. Thank you so much.